Hello. Welcome to the first online class for my class, Quantum Mechanics. We will try to follow to resolve some problems today, following the program of quantum mechanics. In the previous classes, we saw some aspects regarding the Dirac delta potential. We started to obtain the mean values of the operators opposition and momentum, and we also wanted to see the covariances for the position of momentum operators. So as you might remember, our operators x and p we wanted to obtain their mean values using our solution for the delta potential, which was the square root of k, the exponential of minus k, and the absolute value of the position x. Well, before, I think maybe we can ask if everybody is seeing the recording accordingly, if there is no problem to see the expressions. Can somebody in the chat reply if everything is fine? Okay, well, let's wait a little bit. No, okay. Well, so I will probably assume that everything is fine and continue. So we demonstrate that this wave function was it's fine. Nice, thank you. We demonstrate that this wave function was the solution for the Schrödinger equation. The standard Schrödinger equation. For our delta potential. Sorry. Yes, here we need the psi of x, right? So this was the solution. And we wanted to check the mean values of these operators. So in principle, we demonstrate that in this case, our operators, the mean values operators, it was equal to 0, and in the case of the square of our operators, we wanted to see what were the expressions. So we wanted to check what were the expression of these two mean values. So in principle, to do this, we had to integrate, right? We checked that our mean values were given in terms of our psi vectors, which were the solution of the Schrödinger equation. And in this case, we can put it in terms of an integral from minus infinity to infinity of this x of psi star of x, the conjugate, times x squared psi of x. So we demonstrate that in this case our this mean value was equal to 1 over 2 times this parameter k squared, and in the case of the p we wanted to check a solution, right? So in this case, we can proceed in two different ways, and we can obtain the second derivative of the wave function minus infinity, well, and then integrate the second derivative together with the psi star of x, then minus h r square, the second derivative of psi of x dx square. Or we can also change the representation in which we are working. So instead of, for example, using the position x, we can change to the momentum p, and then express this mean value as also an integral, but in this case of the p, of p square, the probability function of finding the particle in the position in the with momentum p. So the previous class we obtained this probability function. It was something, well, it was k to the 3, well, it was something like this, right? This probability is equal to something like this, k square plus p square, well, proportional to this. And in the case, well, we can just substitute this expression here and obtain our solution. So in principle, these two different ways to obtain the solution must be the same. So I would like for you to do at home some exercises and to check that if you do well to do it well, if you obtain this by this procedure, or for this procedure you obtain the same thing. Well, one thing that you need to be very careful is that as you remember, our wave function was written in terms of the absolute value of the position. So in that case, you need to obtain in the case that you are differentiating with respect to the position, you need to obtain two derivatives of this function, right? The first and the second derivative. So be very careful, because what we started to do needs to deal with the second derivative of the mean value, of the absolute value of the position. So it's not zero, this derivative, and also can lead to many troubles. So as you might remember, the first derivative is equal to the function sine of x. So in principle, if we plot this in terms of x, we will have here equal to 1 for x larger than 0, to minus 1 for h smaller than 0, and 0 for x equal to 0. So in principle, you need to derive this function. So be careful, and also check some literature about this. If you have any troubles, please send me an email. By the way, my email, you can contact me by email using the new address .edu that they have provided for these emergencies. And if you have any suggestions or questions, please let me know. So we will continue. Well, once that you show all these properties for the delta potential, you can think of a different problem, now dealing with not only one delta potential, but with two delta potentials. For example, if we have a potential which is written like this, is attractive because of the minus sign, times a parameter V0, delta x minus a plus delta x plus a. Then we can solve again the Schrödinger equation for this kind of potential. So in principle, if we plot this potential v of x in terms of x, we will have two delta potentials in +1 and in -1. So in principle, if we ask, as we discussed the previous class, for energies larger than 0, we will have something related to the free particle with some, scattering, it is called, because these delta potentials, they will stop the movement of these free particles in a certain way. But most importantly, if we ask for energy for the bounded states, that means for energies smaller than 0, we will have to solve the Schrödinger equation and see the behavior of this. So in principle, we will have in that case our Schrödinger equation. We will have the same terms as always. Psi of x, and this will be equal to the energy times psi, right? So nothing new here. We just put the potential, and if we look, for example, for the solution where the potential doesn't show, that means for any x that is different from plus or minus a, so we will have, these deltas are equal to 0, and then we will have the free particle Hamiltonian, the Schrödinger equation, right? So in that case, we will have this expression equal to E times psi of x, right? So in principle, as this is kind of, as you might remember, all the parts where the energy are smaller than 0, we consider these energies as forbidden. So in principle, if you have a particle that is in this zone, it will start to decrease exponentially. So in that case, we can propose the solution of this Schrödinger equation as a normalization constant times minus k, a parameter k, and dx, right? But this, the exact expression that will take this solution will depend of the region that we are located. So if we separate the regions of our system in 3, the first region will be x smaller than minus a. We'll have minus here. The second here between minus a and a, and the third one here for x larger than a, then we will have different behaviors. So we showed that in the case of, well, let me just let you see it a little bit more. Well, by the way, if you have any questions, please write it on the chat, and I will try to solve them. If everything is fine, also please, if everything is kind of, well, if you have some comments, please also let me know. Okay, so let's continue. So we show that if we are in region 1 or 3, the solution of this will have a certain oh, wait. Okay, so let me erase. We have normalization constant times kx, and psi 3 will be equal to n3 times a minus kx. Well, we discussed in the previous class that these functions, e to the minus kx and a to the kx, satisfy the conditions for the wave function to be integrable. Well, not the wave function, but the probability. The probability must be integrable. And also the integral of this dx over all the space of this probability must be equal to 1. So in principle, we discussed that then that means that the functions, the function psi of x must go to 0 when x goes to plus minus infinity, right? So in principle, these are the solutions that satisfy this condition. And in the case of the space between the a and minus a, so that means for the region 2, we will have something a little bit different. So we will have this kind of solution. Exponential of e to the kx and the exponential of minus kx. So we have the combination of both minus and plus kx. So, well, to obtain these constants n1, n3, a and b, we need to apply the conditions for the continuity of the wave function and the discontinuity of the derivative in the borders of these regions. So, for example, if we are located in x equal to a, we know that the probability to find the particle just before, if we have, for example, x minus epsilon, no, a minus epsilon, and a plus epsilon. For the probabilities in here and here must be continuous if epsilon goes to 0. So that means that our function, wave function, x of a in both regions must be this, the same. So we are in the region. We compare the solutions for the region 2 and 3. Then they must satisfy this continuity of the wave function. The same for the if we are in the position equal to minus a. So in that case, we deal with the psi minus a must be equal to psi 1 of minus a must be equal to psi 2 of minus a. So these are the two conditions that we have. So this is the implies a continuous wave function. And as we saw the previous class, well, some previous classes, if we integrate the Schrödinger equation around these borders of the regions, we can obtain a discontinuity for the derivatives. So we need to integrate from, for example, minus I minus epsilon to minus I plus epsilon in order to take into account the both regions of before and after. That means the region 1 and 3. So we'll have the integral of minus h over m, the second derivative of x squared psi of x minus b0 delta of x minus a plus delta of x plus a times I, and this is equal to a times I of x. So we need to integrate all the expression. If we deal with the first term, the second derivative, it will give us the difference between derivatives in the different regions. In the case of the delta functions, they will only give us the wave function psi of x in minus a. Well, when we yes, in minus a. And in the case of this term of the energy times I, we will have the integral of this I. So in principle, one of the exercises that I want you to do at home is to integrate this Schrödinger equation and to obtain the discontinuity for the derivatives in these regions. So we will have also the same kind of expressions for the other border for x equal to a. So in that case, we will integrate from a minus epsilon to a plus epsilon. The same expression, right? Minus b0 delta x minus a plus delta x plus a. Okay. So, sorry. And this is equal to the energy times psi of x. So, when we get these integrals, we will obtain the limit when epsilon goes to 0. And then we can obtain the expressions for the I'll move a little bit to the, okay, in order to see better. We will have the expression for the discontinuity of the derivative. Okay, so in principle, I want you to do this exercise at home and send me a photo of this exercise to my email. There is also a video that explaining all this stuff in YouTube. I will give you the link at the end of the class, and please, if you have any questions or something was not very clear, try to go to the video, and well, I hope that it can help you. And also, well, there are several exercises, so please try to solve them and send the photos to my email, so I can see if you are understanding all this procedure. But I think there is no big deal with all this, right? It's kind of more or less well known. But if you have any question, please let me know. Okay, so let's continue. So in principle, we will have the expression for the derivatives, and that means a relationship between psi 1 of minus a and psi 2 of minus a. Also a relation between psi 2 of a and psi 3 of a, and the derivatives, right? And also the derivatives. So minus a in region 1 and in region 2. And the same here. So in principle, we can obtain several things from these different expressions. One of the things that we can obtain is the relationship that the k, the global k that was expressed in our solutions here must satisfy. So in principle, the expression, if we use all these equations for the continuity and discontinuity of the derivatives, that results from all this is the following: is the exponential of minus 2ka times is equal to plus minus 1 minus k over k0, where k0 is a function of the potential parameter v0. You can check the details in the video that I will give you at the end of this of the lesson. And normally, well, as you might know, this is called a transcendental equation, because in one place we have k in the exponential, but also in the other place we have k. So it's kind of difficult to just solve this equation by normal standard solution, well, algorithms to solve the standard equation, right? So what we do instead of solving directly is to plot two sides of this equation and see where these plots cross each other, right? So in principle, if we do this, we will have here our variable k. So we know that this exponential is a decreasing function like this. And in the case of the other side, the right side of the equality, we will have only a line with a slope, negative slope, and it will be something like this, right? So in the case, well, in the case that, well, if we have a certain k0, and this k0 gives us a line like this, then we will have only one solution here, is where these two plots coincide. So in principle, we can approximate this solution by just plotting these two functions, right? And this is the k that is solution. But also we can have some other type of behavior. We have k here, and we have our exponential, and also we can have something like this, something that touch the exponential very early, like here, and also here and here. So in this case, we will have two different k's that are solutions. Two k's. So you need to be very aware of what are the values of your parameters in order to check which of these cases you can get. So all this will depend of the number of this k0 that is, well, most importantly of the value of this b0 and of the value of our parameter a. So with these solutions, with this case, we can finally obtain our wave functions psi1, psi2, and psi3, which are all defined in terms of this parameter k. But most importantly, we can obtain the energy, right? Because if you substitute any of these AN functions, well, the functions, wave functions in the Schrödinger equation outside of the borders, that means that, if, for example, if we are in the region 1, we will have something like this. And as is equal, well, the x is different from the border, so different from minus a, then we will have this equal to the energy times psi of x. So you can show that in reality, if you substitute the expression that you obtain for psi I, the energy should be equal to minus h squared k squared over 2m. So that means that if you obtain this case, that are solutions of our transcendental equation, this one, then you will get the energies. So you can only substitute here and see how many energies you will have in your as the solution of your problem. Okay. So well, there are a lot of stuff that we can discuss about all this. But well, one of the things that I would like to express is, for example, in the case that well, that our particle, if one particle, we have one particle here, and we divide our space in our three regions. Here, I, 2, and 3. Then 1 minus k, okay, there y is here plus minus 1 minus k. What we should do with the case minus? Okay, yes. Well, in principle, in the case of minus, we will have, instead of here a negative slope, we will have a positive slope, right? So in that case, we will have here our exponential and something with positive slope, so something like this. So again, the k that satisfy, that cross both functions will be the solution. So and the energy will be the same, right? We will have the energy equal to minus h bar square k square over 2m. So in principle, the solutions will be the same, but we will explain a little bit later that the interpretation of the results will be a little bit different, and is regarding what I wanted to tell about these regions. So I will try to explain a little bit later about the positive case and negative case, the difference between positive and negative. So I don't know if there is another question. Well, we will wait a little bit. So in principle, you should do the same for both positive case and negative case. In the negative case, you have something that goes in a negative slope, and in the positive case, of course, you have positive slope. So, well, okay, nice, very good. Okay, so let's continue a little bit. So, in principle, if a particle is described by these wave functions as solution of this potential, then we can discuss that, for example, if this particle has a predilection to be in if there is some physics that we can explain, if there is a predilection for a certain region of our space. For example, we can think of a particle that offers a certain physical property which give us that our particle will be more in the third region than in the first region. So if we think about it, there is no physical property which gives us that there is a difference between the first and the third one, right? So that means that there must be a kind of symmetry. So, and the same, for example, in the second region, if we take into account the parts here where x is larger than 0, but smaller than a, and x smaller than 0, but also smaller than minus, and larger than minus a, you can are the same thing. If there is a physical mechanism or property which tell us that in this region there will be more probability, or in this region it will be more probability, and you, from only the trigonometric equation, you cannot get if that there is no property that allows you to conclude that there is a predilected region. So in that case, that means that our psi, the complete psi that describes our movement or our system must have a fixed or a given symmetry because of this. Okay, so well, there is only two different kind of symmetry, right? And so that means that psi of x should be either symmetric or antisymmetric. Minus x. So, so we will have two different types of solutions. In the case of well, if we remember the expressions of our solutions, that is this one, and this one. Then this also implies some properties about the normalization constants that we will have. This N1 and N3 and A and B must satisfy certain conditions in terms to satisfy these symmetries. Okay. So okay. So in principle, as we don't have predilence between, well, a predilect region between 1 and 3. That means that N1 should be equal to N3 in order to have the same symmetry. And in the case of there is no predilection between the part, well, the region between minus A and A, between this region and this other region, there is no predilects. So that means that either A must be equal to B in the symmetric case, or A will be equal to minus B in the antisymmetric case. Okay. So, well, so in principle, if we take into account this stuff, we will have then our psi of x will be either symmetrical. We will have psi of x subindex s for the symmetrical, and we will have the following. We will have n1 exponential of kx for x smaller than minus a, smaller than or equal, then a times exponential of kx plus exponential of minus kx for the region 2, that means between a and minus a, and n1 again for the minus kx for the region 3. So are equal to a. So that's the first, well, and of course, if you check the expression for the function at, sorry, here there is a mistake. Okay, here is minus k Oh, okay, nice. No. Okay. Minus kx. So you've checked well the expression for this second region. You can write this in terms of the cosine hyperbolic cosine, right? So the solution will be expressed in terms of the cosine. And in the other case, when we have the antisymmetry, we have that psi of x will be equal to n1 exponential of kx for x smaller or equal to minus a. Then a times a to the kx minus a to the minus kx for the region in between, larger than minus a, or smaller than a. No, the other way around. And n1 again, a to the minus kx for x larger than a. Okay, so in principle, here we have a parenthesis. Also, we look for the expression of in the region number 2. This will also be proportional to the hyperbolic sine of kx. So in principle, using all these arguments, we can obtain the solutions. So one of the things that I want you to do is to plot this type of solutions and see the difference between them, and also to discuss the properties of these solutions. For example, there will be some particular cases where the case are different from this antisymmetric case than from the symmetric case. So that's also a little bit related with this discussion that I told you a little bit before, between these cases of case, right? We will have, for example, a negative slope or a positive slope here. So that's what I want you to know a little bit more. So in principle, you can see well, I don't know if you have any questions about this, because, well, for example, for the double potential, we can explore more properties, but I want to see if everything is going correctly, or if you have any doubts, any questions. Well, we will wait a little bit. And by the way, it's important maybe that you can send me an email, because it can be good that I have your emails in case that well, this can continue for a longer period of time. Mustn't be there minus n minus n1. Let me think about it. Well, in principle, yes. In principle, yes. Can be here, if in order to be completely antisymmetrical, should be minus n1. But what I was thinking actually was for the probability. In the probability, this sign will disappear, but the sign in the minus k will survive. So yes, you're right. To be completely antisymmetrical, should be minus n1. Any other question? It says maybe index isn't A, but must be S. Well, in this case, in the case that we are dealing here, it should be antisymmetrical. And this other case, we put the symmetrical case. So there should be either one A and one S. Yes. Yes, well, they say, I just plotted, and in symmetry case, there is some probability an x equal to 0, but in the antisymmetrical case, there is 0 probability in 0, yes? Well, in principle, if you plot the probabilities, say, well, like this, then you can see that you will have something like this. Well, something like is symmetrical here, right? And also is there is a discontinuity here. So let me just try to plot it a little bit more carefully. So you should be something like this, and then here a discontinuity in the derivative, so it should be something like this. Well, of course, well, I'm not a very good drawer, but something like this. And in the antisymmetrical case, you should have something like this. Well, here is A and minus A, by the way. You will have something like this. And here a discontinuity on the derivative. Well, it's kind of difficult to write it here a little bit discontinuity. Well, it doesn't look like there is a discontinuity, but it should be. So in those cases, well, something similar to this. So, and says near the psi function. Okay, thanks, I got it. Okay, so I think there is no more questions about this. Okay, so in principle, we can also check the expression for the, well, only for plotting this type of solutions, we can already describe or try to describe the systems by these probabilities. We might notice that, for example, in the case of the symmetrical, well, this will be symmetrical and this will be antisymmetrical. As the probability to find the particle is like well, like plus x squared, not I see, yes, okay, yes, thank you, not minus, it's like plus x squared. I see, so it's like this, okay, and the discontinuity is a little bit more evident here. So in principle, there should be something like this. Okay, thank you. Okay, so in principle, yes, and also here, and also here. Yes, let me erase here. Yes, I was only guessing. So in principle, we really plot it, will be something similar. To this. Right. And also, well, here there will be a continuity. But here there will be a discontinuity of the derivative. So we can expect that, for example, as the probability of finding the particle is a little bit bigger in x plus minus a, we can expect that maybe the mean value will be affected by these two probabilities also here. But also, well, we will need to take into account in the antisymmetrical case, the peak that we have at x equal to 0. Okay, so in principle, you can, as an exercise, well, this is a little bit more tricky because you need to be more careful to try to check the expressions for the mean values of x, p, x squared, and p squared, and see how the symmetry and anti-symmetry affect the results. You will have different values. Zero in zero. Yes, well, yes, in principle. So, okay. So in principle, well, you can look for these properties. Okay, so this sine of x squared seems as x2 to x squared 2. Moreover, we must have 0 in 0. Oh, yes, by the way, yes, because we have this expression, right? We have that the cosine square of x minus sine square of x will be equal to 1. So in principle, when we have squares, will be kind of similar. So the behaviors will be a little bit different from the ones that we have plotted. Well, that's the so it seems that both of cases kx is equal to 0. We can find a particle in position 0 in the second case. It's a little bit confusing. Well, this is a little bit was as we discussed in the previous seminars, right? Like, for example, if you have something, well, a probability of finding x, and you will have something that is very regular here. In this case, the maximum probability will be equal to the mean value of x. But in the case that we have something that really depends, we have a difficult dependence on X, right? Like for example, here will be something like this, and then here something like that. It will not, in this case, the maximum of this probability will be different, will be not equal to the mean value. So in the case of, well, it's illustrating this when you plot the probability and see that there is no, there's no probability of finding this particle there is equal to 0, but anyway the mean value takes into account different all different aspects of the probability distribution, so let's not be confused by that. Okay, so is the difference between max probability or the probability itself and the mean value. So I hope that with more experience you will not get confused for this. Okay, so well, so in principle, as I told you, all this is more or less summarized in a video that I uploaded in YouTube. The video is well, I will send you the link of the video if you send me an email, but in the case that you want to watch it right now, you can watch it in this link. Oh, well, maybe I can just show the video here. Let me just write down the link. Okay, this is the link. Well, it's important to follow the capital and lowercase in order to see. You can check some aspects here of the class, and well, let me check if you can hear it. Maybe you can.
In the course by solving the problems in the program.
Okay, let me just start over.
Hello, this is Hulio. Welcome to the first online class. In these classes, we will try to advance in the course by solving the problems in the program. For this purpose, you need to do some exercises in your notebooks and send me a photo to my email in order to check that you are understanding. Let's begin. First of all, let's have a summary about the Dirac delta potential, which we discussed some classes ago in order to check some of the properties. We solved the Schrödinger equation for a Hamiltonian with potential given by the expression. We had shown that there is only a balanced state, which is solution to the Schrödinger equation with wave function equal to, with k being a positive constant. If we substitute this expression on the time-independent Schrödinger equation, and then use the following expressions for the derivatives of the wave function, where the sine function is defined as, one finds that the energy can only be equal to, which is the only allowed energy, which sat expression for the second derivative of psi of x by examining the derivative of the function sine of x. Exercise 2. Check the expressions for the energy and k from the Schrödinger equation, from the expressions for the wave function and its derivative.
Okay.
One can check that the mean values of the position.
Well, yes, I will stop a little bit. I'm trying to write on the chat, but I cannot Just let me give a second. Here. Yes, nice. Okay, so I will just copy the link here. No, here. Where is it? Let me copy the link and let me send them. No, I think it's the
momentum.
And there is no way. Okay, I will try to write it. Let me check only if I can do it. No, it's not this one. So, well, seems like no. I will try to solve all these problems for the next class. But anyway, if you have some questions, well, I can write it again here, and try to see if it works. So is YouTube is youtube.com/watch, then question mark B equal to C capital C, lowercase b, 7 EN, N capital, I lowercase, 6 U lowercase, J uppercase, and K lowercase. So, well, we will check all this stuff by the next lesson. I hope that we can just solve all these kind of problems for the next lesson. So, well, we can proceed using all this stuff. Well, we can well, if you want, you can check the video, and if you have any questions to ask me, or if you have the question right now, just to try to interact a little bit more right now. No. No. So in principle, we will try to solve all this. Okay, so I think then maybe there is no questions here. Everything is clear now. Okay, very good. So in principle, I would like maybe to discuss some other stuff, but probably is better if we leave it for today, as there is a lot of information actually that we didn't discuss. And for example, you can see that in the video there is this kind of exercises. So I'm more interested in seeing if you can solve them correctly, and well, if you have any questions about this topic. And in the next class, we will begin to discuss the harmonic oscillator. So as it's also a very different kind of topic, maybe it's better to continue the next lesson, in order not to also have too much material and be more confused sometimes. So please try to solve all these exercises that are on the video. If you have also any comments, please comment on the video itself, or if you have some other stuff, you can send me the email, and don't forget to send me the photos of the solutions. So, and if everything is fine, maybe we can just finish for this lesson. So, yes, well, we will wait a little bit, and in principle, if not, then we will continue next class. We will wait a little bit. Yes, well, yes. So we must send some exercises. Yes, in principle, what I wanted to do is for you to solve these exercises. Even if you cannot do it, just send me what you are doing. Well, what you have in your notebook, because in that case, I can notice if there is some problems, or if there is some things that I need to emphasize. And as I cannot interact with you very clearly, it will be more difficult. So that's the reason that why I asking for photos. Okay, and that's fine. Thank you. Okay, so in principle, if there are no more questions, then I will see you the next class, the next Friday, and also don't forget to send me these photos, and most importantly, try to stay at home to follow all the considerations about this virus, and stay safe. So I would like to wish you good luck, and that's goodbye for me for now. Bye bye.